All right, let's dive right in. Today, we're going to unpack one of the most vital processes in all of physiology, how your neurons talk to each other. Seriously, this is the basis for every single thought, every movement, every feeling you have. So, let's get into it.
I mean, really think about that for a second. You decide to wiggle your toe, and almost instantly it happens. That signal has to travel from your brain, down your spine, all the way to your foot. It's an incredible distance, and it happens in the blink of an eye without the message getting garbled. So, how does the body pull off this amazing feat of engineering? Well, that's the puzzle we're going to solve today.
Now, to really appreciate how special the nervous system is, let's quickly put it side by side with the body's other big communication network, the endocrine system. The endocrine system is kind of like the body's wireless network. It sends hormones to the bloodstream. It's powerful for sure, but it's slow. We're talking minutes, even hours. The nervous system, though, that's the wired system. It uses dedicated cables, our neurons, to shoot electrical signals at incredible speeds. When you need rapid, precise control, this is the system you use. It is absolutely built for speed.
Okay, so to understand how a neuron fires, we first have to get a handle on how it rests. Because a resting neuron isn't just chilling out. It's like a coiled spring, packed with a huge amount of potential energy, just waiting for the right trigger to be pulled. And this state of readiness has a name, the resting membrane potential. You can think of it as a tiny electrical charge across the neuron's membrane, basically a microscopic battery. This separation of positive and negative charges is the stored energy that's going to power the whole show.
So, how much juice is in that battery? Well, in a typical neuron, it sits at about negative 70 millivolts. And the most important part of that number is the negative sign. It tells you that the inside of the cell is negatively charged compared to the outside. This is our baseline, the quiet before the electrical storm. So how does the neuron build and hold this negative charge? Well, it comes down to two main players. First, you've got these potassium leak channels. See, the cell is packed with positively charged potassium ions, and these channels are always open, so potassium is constantly leaking out. As all that positive charge leaves, the inside of the cell becomes negative. But that can't go on forever, which brings us to player number 2, the sodium-potassium pump. Think of this as the battery charger. It's constantly working, using energy to pump sodium out and potassium back in, making sure those gradients stay strong so the whole system is ready to go.
All right, the stage is set. Let's get to the star of the show, the action potential. This is the signal. It's a very brief, massive, all-or-nothing electrical pulse that can race down the entire length of a neuron without fading away. This is the body's answer to that long-distance communication problem.
And this graph right here is our roadmap. Look at the far left. That flat line is our resting potential, sitting nicely at negative 70. But when a stimulus hits, bam! Look at that curve just shoot upward. It doesn't just get back to zero, it rockets past it, making the inside of the neuron positive, peaking at around plus 30 millivolts. Then, just as fast as it went up, it plummets back down, even dipping below resting for a moment before it levels out. We're going to walk through exactly what's happening, piece by piece, along this incredible spike. But first, a critical rule, the all or none law. A neuron doesn't fire a weak signal or a strong signal. The stimulus has to be strong enough to push the neuron to a critical tipping point called the threshold, which is right around negative 55 millivolts. If you don't hit that threshold, nothing happens. It's a dud. But if you do hit it, you get the whole fireworks show, the full identical action potential every single time. It's like firing a gun. You can't half pull the trigger.
Okay, let's zoom in on the machinery. When the neuron is resting, the most important channels, these voltage-gated sodium and potassium channels, are closed. The sodium channel is in this weird state where it's closed, but it's totally capable of opening. It's just waiting, primed and ready for action.
Now, when that stimulus pushes the membrane to threshold, that change in voltage makes the sodium channel's activation gate fly open. And this sets off an incredible positive feedback loop. Positively charged sodium ions flood into the cell, which makes the inside even more positive. And that positivity opens even more sodium channels, causing this explosive runaway rush of sodium into the cell. This is what creates that steep rising part of our graph. That's depolarization. So at the very peak of the action potential, two things happen almost at once. First, the sodium channel has a second, slower gate, an inactivation gate that swings shut, plugging the channel. No more sodium can get in. At the same time, the slower voltage-gated potassium channels finally swing open. So now you've stopped the sodium from coming in and you've opened the floodgates for potassium to rush out. All that positive charge leaving is what makes the membrane potential crash back down. That's the falling phase or repolarization. You might be wondering,
Well, why doesn't the signal just go backward? Great question. It's because of something called the refractory period. Right after firing, that patch of membrane is totally unresponsive for a little bit because its sodium channels are inactivated. They have to reset. This basically creates a one-way street for the signal, forcing it to keep moving forward, away from where it started.
So our action potential has brilliantly traveled the whole length of the neuron. Awesome. But now it's at the end of the line, and it's facing a new problem. There's a tiny gap, the synapse, between it and the next cell. How on earth does the signal get across that divide?
It can't just jump. The electrical signal can't cross that gap, which we call the synaptic cleft. So the neuron does something truly incredible. It converts the signal. The electrical message, the action potential, gets translated into a chemical message to cross the gap. Then, on the other side, it gets translated back into an electrical signal. This amazing little translation station is called the chemical synapse.
Here's how that handoff works, step by step. First, our action potential arrives at the end of the axon. Second, that voltage change opens up calcium channels, and calcium rushes in. Third, that influx of calcium is the trigger. It tells these little bubbles full of chemicals, called synaptic vesicles, to release their contents, the neurotransmitters, into the gap. Fourth, those neurotransmitter molecules float across the gap and lock onto receptors on the next neuron. And finally, fifth, that binding opens up new channels on the receiving cell, creating a new electrical signal and completing the pass.
So the signal made it across the gap. But we're not quite done. The receiving neuron isn't just a passive sponge. Nope, it's more like a bouncer at a club. It's getting thousands of signals, some saying go and some saying stop, and it has to add them all up to make a final decision. Does it fire its own action potential, or does it stay quiet?
These incoming signals basically come in two flavors. You have EPSTs, or excitatory postsynaptic potentials. These are the go signals. They cause a small depolarization, nudging the neuron a little bit closer to its firing threshold. Then you have IPSPs, or inhibitory postsynaptic potentials. These are the stop signals. They do the opposite, making the cell's interior even more negative, moving it further away from threshold and making it harder to fire.
Now, a single little go signal, a single EPSP, is almost never enough to get the job done. As you can see here, a neuron is constantly being bombarded by signals from thousands of other neurons. It's got to add up all these little pushes, the EPSPs, and all the little pulls, the IPSPs, to figure out what to do. And this whole process of adding things up is called summation.
The neuron is basically doing math in two ways. There's temporal summation, that's summation over time. It's like one person knocking on a door over and over again really fast, where the knocks add up. Then there's spatial summation, summation over space. That's like a bunch of different people all knocking on different doors at the exact same time. Either way, the goal is to make enough noise to get the neuron to its firing threshold.
The result of all this cellular arithmetic is what we call the grand postsynaptic potential, or GPSP. It's the total combined sum of every single excitatory and inhibitory signal at any given moment. And this is the bottom line. If that final sum, the GPSP, is strong enough to push the neuron to threshold, then and only then will it fire its own action potential and pass the message along.
So let's just end with this idea. We've seen how a single neuron acts like a tiny, sophisticated computer, adding up thousands of inputs to make one simple, binary decision, yes or no, fire or don't fire. Now, if one neuron is doing all that, what does that say about the computational power of your brain, with its trillions of these connections, all making these calculations at the same time? That incredible, buzzy network, that's the very fabric of who you are.